Good morning, everyone. My name is Pierre Siccardi. I'm product analyst for Alkon, and today we're going to discuss how to optimize concrete deliveries using machine learning and concrete trucks equipped with the sensors. So first thing first, Alkon has been developing for more than a decade what we call an in-transit monitoring system that is built around different sensors, and the main one is a slump probe. So it's like a big steel piece that is attached to the surface of the drum. You've got a picture of it here, and every time the drum is doing a revolution, the slump probe goes through the concrete, it deforms, and based on those deformations, we can estimate the slump value. All of those data that are produced are collected wireless to a tablet. There's displays, there's a flow meter. All the data are sent to the cloud as well. And since recently, we as well got an air content sensor. So Alkon is obviously not the only one company doing those kind of sensors. There's Verified, Sidra, and that's great because we are not alone in this field. As I said, the system itself is collecting a couple of different properties. You've got a list of them here. We've got the RPM of the drum, the turn count, volume of concrete, production status, temperature, air content. But what interests us the most today is the slump. At the bottom of the slide, you've got what the customer can see on a website. So it's basically a typical load of concrete. We've got time at the bottom, the RPM of the truck, and you can notice that at the very beginning we've got the loading and mixing at high RPM. Then we've got transportation, arrival on site, remixing, and unloading. So then, if we add the slump value on that kind of graphic in red, you can really notice that during transportation the concrete losses slump, and then when the truck arrived on site, we have an increase in slump. So thanks to the in-transit monitoring, we can as well detect water addition. And for that specific load, the driver just added 20 gallons of water, which caused the slump increased. So that's a typical case of of a retempering method. And considering the amount of properties we collect and the number of trucks equipped in North America, we are clearly in the field of big data. It's millions of data points that are flowing through the systems. A couple of years ago, I've been part of a research project with Laval University. So I did my PhD at Laval University, and it was in collaboration with Alkon and Béton Provincial, which is who's a local producer of concrete in the province of Quebec. And so there was many different topics, many students involved, and one part of my PhD was to study if there would be an interest of employing machine learning methods with the data produced by the network of probes. So to answer that questions, I had to find a topic to study and to do a proof of concept on it, and I chose retempering. So as I said earlier, during the transportation from the plant to the job site, you lose concrete, and this is relative to the mix design itself, the temperature, and so it's the concrete itself and outside effect. We've got traffic, we've got weather that might impact the way the slump is lost. And according to a study by master builders, the need of retempering, the need of adding water to increase the slump and get the right slump, it happens 45% on average of concrete loads. So that's a lot, and it's quite costly. On average, it takes 10 minutes, and it's $30 per every load. So I was wondering, could we predict the evolution of slump based on multiple input during transportation to avoid this need of retempering? And as a real-world solution, we already have the tablet and the system showing the slump at site, let's say like 6 inches. The aim or the use of that model would be to inform the truck driver that at plant you need to be at 8 inches or 90 inches based on the concrete you just batch and the outside conditions. And the perspectives are numerous, but mainly the idea behind that is to have a decision and support tool for the drivers, the plant operators, and in the end improve the production automation. So now let's focus on our algorithm. So as you can notice on that slide, I called it a slump anticipation algorithm because we want the slump at the plant. And that's my output. What would be the target slump at departure based on many different inputs. So for that study, I did add the load volume, the concrete temperature, water cement ratio, age at departure. Slump at arrival, based on past data, this is what the system measured, but if we want to use that model in the real life, that would be my target slump at arrival. Travel time, based on past data, again, we know when the truck left the plant, we know when it arrived at the site, so we got it. But in the final solution, we can get it from APIs, like coming from Google Maps or that kind of things. And as well, I did consider the outside temperature and humidity. I know that it's not perfect, as everybody knows in the room. Mix design or aggregate moisture will influence that evolution, but I didn't have the data at that time, so I didn't add it as an input. But in the future, that would be great to input it. And for that study, I did use many different popular machine learning models. You got a list: XGBoost, neural network, Ridge, Lasso, everything. Mainly when you are working with tabular data, XGBoost solves 90% of your problem, and that's easily available and for free, so it's not so. If I continue, this is the data set I used, around 1,600 loads of concrete, and as always in this kind of situation, I had to cut my data set in 2 parts, test and train, and this is the performance I had at that time. So the graphic, it compares observed slump at departure and predicted slump. You can see that the correlation coefficient is quite good, so we can say it works. But right now, like you are wondering, the guy's just presenting for 10 minutes, he's already at the conclusion, so there may be something wrong. So I really want to take advantage of that presentation to show you 2 things. The first one is the dark side of machine learning, the thing that we do not really show in presentation. And the other one is give some basic tool and awareness to people that do not deal with machine learning on a daily basis. So let's get back to our data set. The 1,600 loads of concrete, it was in fact only 30% of the whole data set. That's only the tip of the iceberg. And for that study, I had nearly 5,000 instances, and 40% of them were incomplete, 16% of them were outliers, and 15% of them were instances where the arrival slump was greater than departure slump. And at that time, the producer were picked the data. He had issues with certain admixture and super P, which were taking longer to be effective. So that's why. And the whole part of showing that is most of the time the people, they do not show you that part of it. They just shave the data, just take the part that interested them and work with them. And in that situation, it's easier to get good performance. And again, that was a proof of concept. The intent of it was not to have a final solution, so I felt comfortable doing that. Next, if we continue, let's get back to our performance. And usually people say, yeah, we've got a correlation coefficient of 0.81. And for the sake of the presentation, I'll continue by having the trained data set in red, test data set in green, and usually what people show you, it's the only test data set, the performance of the test data set. And in fact, when you do machine learning, you got a correlation coefficient for both train and test set, and that is really important to have those two values. And in our case, we can say that those two values are quite close and relatively high, and that's a good situation. Let me explain you why. So again, for the sake of clarity, we're gonna transform our multi-input model to a very classic two-dimensional representation. You see it on the left. We got input as x-axis, output as y-axis. Let's put the trained data on it. Now that we got our trained data, we can train our model, and based on those two things, we can calculate our correlation coefficient on the trained data set. Next, if I add my test data, we can calculate the correlation coefficient between our model and the test data set. If I keep those two values and I compare it to a more simplistic model, let's take a linear model. In that situation, I will get a lower value of correlation of coefficient for train and test data set. And that's a case of underfitting. The model is too simplistic to get the main tendency in the data. On the other hand, if I go to a very sophisticated model, I can get to that situation where the model is really able to find the tiny differences, tiny variation in the data set, but it's not really able to replicate well on test data set. And again, that's not a good situation. That's a case of overfitting. So you really want to seek that balance between the two of them. Obviously, there's other metrics to look at it, but I thought it was important to give this kind of slides. Again, in machine learning, we always hear machine learning is like a black box. And I'm not really, I do not agree completely to that statement. And to show you why, I'm going to present a parametric study that we did with two different models, so it's reverse engineering. To do that parametric study, we had to choose some scenarios. So by scenario, it's setting some values for our inputs in our model. And the one important here is slump at arrival, 150 millimeters. And then we can ask the different model what would be the answer of the model based on those values. So you've got the slump at departure on the y-axis, travel time on the x-axis for two outside temperature and for XG boost, one model. So when the travel time increases, the slump at departure increases. So that's quite logical. Next, if I continue, and I put one neural network, which is another type of model, for the lower outside temperature, we've got the same tendency. And if we continue at 25 degrees Celsius, we can see that for the neural network, the slope is the opposite. So at the very beginning, when you see that, you can say, yes, it's not logical. It's not how the concrete behaves. But still, what you have to understand is that it still translates a behavior present in your data set. In that case, maybe we can think about this particular customer having a big construction site 30 minutes away from the plant, and he used a lot of retarder in that specific mixes for higher temperatures. That might be an answer, but still, that's a behavior present in the data set. So 2 things to conclude on that slide. Different models might yield different results, and we still need to understand the concrete science if we want to have something useful in the end. So that's the last slide of my presentation. First, you need to look for convincing results and limited error, but stay critical and be alert. So thanks for your attention, and I'm ready for questions if you have some.
Hi, thank you so much for your presentation. It's very interesting and very nice. I have a question regarding your input variables. So most of your input variables are time dependent. How did you account for that when you develop your machine learning models?
If I go back to that slide, you say they are time dependent, those inputs?
Yeah,
is that
like
your
the
question?
temperature, yeah, humidity.
So for load volume, it's a batch load volume. Concrete temperature, that was the concrete temperature when departure, when the truck left the plant. Water cement ratio, exact cement. Age at departure, we got it. Slump at arrival, it's when the truck arrived at site, the first slump that is measured. Travel time, it's the time between departure and net. And outside temperature, outside humidity, I picked the temperature and humidity at the departure from plant from national big database of temperature and humidity based on location of the truck.
That makes sense. And I have another question. So we might know that slump is a very variable measure. And how did you account for the variability of this variable? And
if I switch to, I think I got something about that. As I said, you can look at correlation of coefficient, but another interesting metric is the root mean square error. In my case, at the performance, I had 21 millimeter of error. And if we have a look at the ASTM standard for a slump of 3.5 inch, you've got 1.1 inch of acceptable range. So based on the error yielded by the model, I can say that I'm lower than the variability of the test itself. So I'm quite comfortable saying that it performs well.
Yeah, that's really wonderful. So for your input data, do you have replicate results for the slump, or do you just have one slump for each tree?
One slump for each.
Okay. Thank you.
Yeah. So,
Thank you, Pierre. Monsef Nedi from McMaster University. I may have missed it, but is your database from one single batch plant or for multiple batch plants?
yeah, it was one batch plant from one customer, and we can, obviously the next step would be to take from others and...
Yeah, no, this is nice work. The issue with slump prediction is not when things work well. When things work well, like the AI model will always predict the trends in the data. So when things work well, people in the batch plant usually they have experience, and there won't be a problem. The problem is when things don't work well, and usually when there is cement admixtures compatibility issues. So it's not reflected well in the data, like alkalis going up, C3A going up, something going wrong, metering at the batch plant doesn't work. And that's when you see those 16% of maybe outliers showing up and creating the issues.
Exact. So and this is why as well, when we train those models, there's some periodicity you have to retrain, because obviously your raw materials are evolving, and if you want to take that into consideration, you have to keep constant retraining and